Hey there, welcome. Today, we're going to tackle a core concept from algebra, multiplying complex numbers. And I promise you, by the end of this, you'll see it's actually way more straightforward than it sounds. Okay, let's just dive right in. See this problem on the screen? Our entire goal for the next few minutes is to solve this exact problem. We're going to break it down piece by piece so that an equation like this won't look intimidating at all. And you know what the best part is? If you've ever multiplied expressions with an x in them in your algebra class, well, you already have pretty much all the skills you're gonna need. Seriously, you're not starting from scratch here. So check this out. On the left, you've got something you've probably seen a million times, right? Multiplying binomials using the FOIL method. And on the right, that's our problem for today. The big secret is, there is no secret. The process is exactly the same. We are still just gonna use FOIL. But I did say you were almost all the way there. There is one new, special little twist. It's a single, super important detail that makes complex numbers, well, complex numbers. And it's the key to getting these things right every single time. That twist, it all comes down to this one little term right here, I squared. Now, you know the letter I is our imaginary unit. But the most important thing for today is figuring out what happens when you square it. It's -1. That's it. That is the entire secret. This weird, abstract idea of an imaginary number squared, it just simplifies down to the number -1. So here it is. Let's call it the golden rule. Anytime, anywhere you see an I squared pop up in your work, you have to replace it with -1. This isn't just a suggestion, okay? It is the fundamental step that makes the whole problem work out. All right, enough with the theory. Let's get our hands dirty and see how this golden rule actually works in practice. We'll start with a basic example and then kind of ramp it up. Okay, first up, let's just distribute a single term. We've got 2i times the quantity 3 minus 4i. So first step, we distribute just like we always do. That gives us 6i minus 8i squared. And boom, there it is, that I squared. The second you see it, you apply the golden rule. We replace it with -1. So now we have 6i minus 8 times -1, which of course becomes 6i plus 8. And for the final answer, we just write the real part first, so it's 8 plus 6i. Now let's try a full-on FOIL example. Remember FOIL? First, outer, inner, last. Multiplying that all out gives us 8 minus 4i plus 12i minus 6i squared. First things first, let's combine the like terms in the middle. -4i plus 12i gives us a positive 8i. And look what we have at the end, our old friend I squared. Time for the golden rule. We replace it with -1. That turns the -6 into a +6. And now just add that to the 8 we already have, and our final answer is 14 plus 8i. See? Not so bad. So what happens when you have to square a complex binomial? This is where a really common mistake trips people up. The absolute most important first step is to expand it. You have to write it out twice, side by side. Whatever you do, do not just distribute that little 2 exponent. Once it's written out, hey, it's just another FOIL problem. We FOIL it out, combine those middle terms to get -12i, and, you guessed it, there's an I squared. We replace that with -1, turning the +4 into a -4. Finally, 9 minus 4 is 5, for a final answer of 5 minus 12i. Okay, so we've seen how to do it the right way. Now let's talk about the wrong way. Let's quickly go over the most common traps so you can be sure to avoid them. There are really 2 major mistakes people make. The first one is super simple. Just forgetting the golden rule and leaving an I squared in the final answer. You can't do that. It's like leaving an answer as 2 plus 2 instead of just writing 4. You have to simplify it. The second is a classic algebra mistake, sometimes called the freshman's dream. And this slide just lays it out perfectly. The wrong way is thinking you can just distribute that exponent across the minus sign. You absolutely cannot do that. If you do, you completely miss out on those middle O and I terms from FOIL. The only correct way is to expand the expression first, write it out twice, and then use the full FOIL method. So you've totally got the mechanics down now, but you might still be sitting there thinking, okay, but why? Why does any of this actually matter? Well, this is where it all gets really, really cool. This is math that actually rotates reality. Here's the big idea. When you multiply by a normal number, you're usually just scaling something. You're making it bigger or smaller. But when you multiply by I, you aren't scaling. You are rotating. Every single time you multiply by I, you are performing a perfect 90-degree counterclockwise turn. And where does that show up in the real world? All over the place. Think about video games. How does a game engine make a character or a car turn so smoothly? It's using the principles of complex number multiplication. Same thing for robotics. These calculations are what control the super precise rotational movements of a robotic arm. This isn't just numbers on a page, it's the code that makes things turn in both our virtual and our physical worlds. Which brings us to one last little thought to chew on. We've just seen that in the world of complex numbers, multiplication is actually rotation. So that kind of begs the question, doesn't it? If multiplication can rotate things, what powerful operation do you think division can do? Something to think about. Thanks so much for watching.